All right. So we'll try to keep this at the, graduate level or college or, no, just kidding. We're going to talk about complex systems at a human level. And actually, I think that's really important because that's the part of the system that we are. So we are going to talk really about how coordination is introduced into systems. That is interesting. Here we go. We are going to talk about how the coordination is introduced to systems, accounting for the communities, accounting for the natural elements of the system, and accounting for the parts of the system that we've introduced ourselves. And in fact, you always want to start with our goals, and as Rutger mentioned, we want communities of local actors, and we want them to coordinate using technology. Apologies, I'm getting a little bit of a hang of the clicker here. Cool. So the first part of my talk is going to aim to educate. We're going to talk about complex network systems and sort of set a basis for how we can think about these interconnected systems with multiple layers. And that requires us to sort of take a step back and examine sort of the different tools that come to play and use them to understand systems in sort of a holistic sense. And I usually start with thinking about structure and flows. So a network characterizes structure. It's the way things interact with one another, and we use system theory to understand the flow of things through that structure. When we start to bring ourselves into the system, we have to think about how the world works in terms of generally nonlinear systems, and the game theory and mechanism design tends to be the tools we use to examine our own interaction with the way those systems work. And as we sort of build these systems or examine these systems, we start to see things that are interesting emerging, right? There are patterns. We start to see collective behavior, and ultimately the collective behavior itself might change, and we can think of that as evolution and adaptation. In the case of these complex systems, though, we have sort of multiple layers we've walked through, right? The structures and flows, our interactions with the system itself, and the patterns that come from that. As we step into this, we have to think about the elements, the silos that we've traditionally thought about when problem-solving systems. We have the social elements. We kind of start with ourselves. We're very sort of self-centered naturally as a species, right? Well, what does it do for me? But in reality, we have these systems that are made up of many silos, and we examine them each as their own field. We look at the economics as the value flows. We look at the technology, that sort of the augmentation of the physical world, and then we have the physical world itself as it existed before we began to augment it. But in order to look at a system holistically, you can't slice it into these silos. You have to kind of step back and ask, what does it take to design for all of them together? How are they interconnected already? And make sure that the solutions that we build respect those interconnections. And we ask what we're trying to accomplish in a very global macro sense. But you don't build solutions at the macro level. I mean, to be honest with you, when you talk only macro, it kind of feels fuzzy and you're not making anything. So you have to work your way down and understand what it takes to get to those macro views. And we do that by asking, well, what kind of local behavior results in the macro trends that we want? Well, we can't guarantee that people are going to do what we want them to do, but we can step down again and we can say, well, what are you allowed to do, right? We can start to control that. We're building the system, especially when we're bringing cryptography into the question, where we have trusted computation, and we can say, well, you can do this, you can't do that. Well, turns out that's also how the real world works, right? We have the laws of physics. You can do some things, you can't do other. And any behavior that actually emerges is still predicated by what's actually possible in the first place. And in fact, that itself is well defined over the state of the world. Like, the world is made up of matter and energy, and to some extent, it's in some states, and that's what things are. And so we have a whole stack now that goes all the way from the bottom level of sort of what it means to be in a particular state, up through what it means to change the state, up through sort of what we're going to build to explicitly allow, back up to what people do with that allowance, and up to the macro flows. And so we need to basically step away from our siloed view of these systems towards a hierarchical view where in each layer we understand the interconnectedness between each of the silos. And obviously this is a model, it's a way of viewing the world, but it's one that's really useful for building things, and it's useful for building things in a way that's sort of aligned with the way nature's constructed up from sort of its basic states all the way to the sort of flows within the world that we observe and sort of think of as working. And in this case, we're saying each of the lower levels enables the one above it. I think that it's important to take a step back when we're talking about decentralization and realize this analogy to nature is a little bit deeper even. Nature actually is decentralized, like it's matter and energy spread out in space and evolving in time. There isn't a global state of the world. There is only an interpretation of the global state of the world that we impose on it. So when we mimic nature with these systems, we actually do a better job making decentralized systems because we don't have to do something special. We say, like, how do we construct things up? And we don't have the downward logic that tended to be used in a lot of our technological architectures top-down. We say, well, we want it to do this, let's make it do that. Nature doesn't have that property, so when we use nature to design decentralized systems, we actually do a better job. Maybe the crux of it is every behavior that you exhibit is a byproduct of local observations, local actions, local changes to the state. I like to say if I throw you a baseball, you have it and I don't, that's the same as a no double spend. It's literally a conservation law, you can't violate it, you're building on basic logical principles of physics. So then, like, taking a step back and realize we actually already have some decentralized systems that we've constructed. You know, the international sort of airflow, air traffic is, you know, loosely, locally orchestrated. You have air traffic controllers in an individual airport making sure airplanes aren't crashing into each other when they're physically in the same place. But you don't have to worry about them crashing into each other if they're on opposite sides of the world. So a big part of the system that you're actually orchestrating is still local when viewed at a macro scale, and we can sort of step in and look at a micro scale and say, well, I live near Berkeley in California, and I got here by flying from California by way of Dallas after taking a, mass transit to the airport and taking a ride share down from Amsterdam. So again, none of the elements of this cared about the other elements. I physically moved through space in a very decentralized way. And I think it's important for us to remember that we actually have real structural decentralized systems that we made already, and we understand them pretty well. And we can even use those to recognize our own means of augmenting. So we want to talk about how this is accomplished when we want to build these things. Well, in the case of blockchain-enabled systems, we really don't need to think about blockchain at all, per se. What we really need is to fill in the layers. And so, this is going to ask the same sort of questions, where we start at the ecosystem level, flows, the roles in the system, the stakeholders, how value flows between them structurally. And we can ask what kinds of pairwise or lower level micro interactions are required to have that make sense. And we can then sort of say, okay, well, now that I know what my protocols are going to be at the interaction pattern level, like what I need to do to engage with you, then if I want to do this without a centralized governing body or a platform, then I need something else to do the validation of my rules of physics equivalent, right? So we do this with a peer-to-peer network. It's a decentralized computation and communication network. So we're just basically sharing messages with cryptography and saying, well, whatever it is that I need to say to ensure that the system above actually is trusted in a computation sense. And in fact, that communication and computation network relies on software. And so someone has to create that software. It defines the rules of what it means to participate in the peer-to-peer network. And what's interesting about this is that while it's mixtures of sort of networks of sort of communities, like entities participating with each other, and then software that allows something, it's not community, software, software. It's community, software, community, software. It's mixed. It's a layer cake. We've gone from what was that we imagine the evolution or ecology of the community, and then the software that allows those behaviors then the community that enforces the correct use of the software the level above, and then sort of the lowest level of software, which is just creating the rules for that coordination, for that communication. So there's two distinct layers of coordination problem actually appearing here, and we actually have to separate them if we want to get them right, because one creates the physics and the other creates things under physics. And the way that we sort of think about the two layers in the technological sense is when we're doing interaction patterns, the rules about how we engage with each other, we can think about things in terms of those conservation laws. And so I have an example here. It's a little bit abstracted, but it basically imagines that a good is going to be exchanged for a service, but that there are some positive and negative externalities exposed by this. It might be pollution generation, and then on the flip side, there might be some positive social impacts because you're helping your friends. And you have both a positive and negative externality, which in a traditional sort of just pricing market model would be completely lost. It's missing from the structure of the problem. The impact occurs anyway, but if it's not actually accounted for in the action that is taken in the price, then it won't be reflected in the behavior, and therefore the system will literally not account for it. People will sort of optimize on their local objectives, and this constraint is missing, and we lead to things like large amounts of pollution or sort of adverse effects on systems simply caused by missing structure. The underlying natural system has a structure. There's a real dependency, but the financial or economic system that you're leveraging, the pay for service, ignores a structural element. And we actually see a lot of our systemic breakdowns in our current society can come from parts of the system that we know intuitively or even scientifically are there, and our economic system ignores them, maybe because we don't have the tools or the means to account for them properly. But nonetheless, that structural misalignment makes it so that the optimization that's achieved by the sort of economic behavior actually drives the system into an undesirable state rather than into a desirable one. And it's my hope that we can address that through sort of cryptographically empowered technologies. I don't generally jump to blockchain because blockchain is we've talked about its hype. It's a great example. It sort of was a proving ground for this idea of durable state and verifiable computation. But at the lowest level, what we really need is trustworthy data. If we know that the data that we have represents, we won't even say truth because it could capture subjective data, and it's meaningful to have subjective data because you can have various interpretations. But we know that it's history. We know it's provenance. It was logged at this time. If I go to get it later, I know that it's the thing that I thought it was. And we do this through content addressable DHTs. We can do this through DAG structures, not necessarily in the blockchain DAG sense, but a directed acyclic graph just means that there's sort of this ordered reference where you know that something came before something else, and you can know this cryptographically as long as you have a reference, because you can't reference a thing with its hash if it didn't exist when you wanted to reference it. And so you get this sort of attribution, and you can even add in attestation, meaning that someone might reference a thing with a yes, this is true, or a no, this is false. And you don't actually have to even a priori decide how to interpret that. So we have some pretty powerful tools from a data structure and trust perspective. We really are just figuring out how to use them. And actually, one of the things that I'm most excited about is what it means to get these sort of flexible but provable, sort of not pre-interpreted, lowest levels of data into place, and then we can build up on top of them. And things like blockchains are great for holding information that everyone needs to know. So they might even hold the rules about how to use a system that's a little bit more general, because as a redundant database, you almost only want it to hold the things that everybody needs to know, because otherwise you're wasting energy, it's not an efficient use of the resource. So I think the tools are really exciting. I think new tools are coming, and I think that we should really look at them in terms of the systemic structures. That's why we come at this from a complex systems perspective. We kind of know what we need, and we use what we have, and we also can push forward to find the new things that we need to fill in those roles in the stack better. And so we're going to take a step back to the concrete and look at what these whole systems are in the physical world. So I like the transportation network a lot because it's our decentralized physical system that we made and has nice natural laws. And so when we talk about the difference between the nature of the system, the physical stuff. We have the cars and the roads, and ultimately they dictate what you can do. I mean, you can drive your car off a cliff if you want to, you're not going to. So you get to the second layer, and you talk about norms, and you talk about laws, and you say, okay, well, given all of the things that physics would allow me to do with the roads and the cars, like there's a much smaller set of things you're actually going to do, which is more or less follow the laws, avoid running into each other, and eventually the combination of the what you can do and the sort of behavioral elements give us traffic. Maybe not ideal, but it's the emergent property of us having cars and roads and us participating in that infrastructure as active agents. And what's interesting is now we have this sort of new additive adaptation sort of coming. I don't know how fast it's coming, but people are doing some research. There's some autonomous cars that are running around, done tests in California near where I live, and in Arizona, where I also travel regularly. Good test beds for these. And really what's happening here is we're exploring the automation of the will-do layer. Like we're taking away some of the autonomy, or excuse me, the agency of the driver and giving it to a software system, and then we're saying, well, what will you do? Well, the car is going to drive the speed limit. It's going to follow collision avoidance, which we were doing anyway, hopefully. But this is a little bit like introducing smart contracts, because we're saying this layer is governed by this piece of software. And incidentally, though, what the will do becomes is whether you participate at all, right? If the car is going to drive itself, I still get to decide whether to get in it or where to tell it to take me. So we're not actually getting rid of the human element, we're changing its role. And it means that the system itself is a new system, different emergent properties, but we're still part of it, and it's still made up by the can-dos and the will-dos and the emergence. So sort of last big section of the talk, we're going to try to inspire you by talking about like where we can take this. Since we know about complex systems now, we sort of understand the role of the technology in creating them. So what about this is like really exciting? Well, for starters, what excites me is this loop between our human part and our world. We didn't really acknowledge this well for the last 10, 20, 100, maybe more years, but when we engineer things, we're adding to the world, and that world is start influencing us, and we're adapting to it. So this closed loop has become really apparent in the last, say, 5 years as our sort of machine learning embedded inside of web apps that we all use actually directly changes our behavior on a really tight loop. And so this relationship is becoming really easy to see, and we need to be a lot more aware of it. And as it happens, I founded a company to help engineer systems because I've been working on sort of complex adaptive systems, swarm intelligence, bio-inspired multi-agent coordination since the early 2000s. And when I first got introduced to this new technology, I got really excited because reality is I could work on robots, and I could work on some infrastructure systems, and I could love modeling human behavior systems, but there were missing interconnections in terms of durable state and computation, trusted computation. You couldn't really design for how to do coordination for humans because you would need this statefulness. You would need this validation of the transitions in order to use the principles that come from the types of multi-agent coordination algorithms that I worked on. And when I really came to terms with the fact that we had stateful information systems, really had the properties of the kinds of robotics and coordination systems I love to work on, I founded a company and started just focusing on what you would consider sort of AI research, but it's sort of decentralized. And I am an engineer by training, so I also think it's really important to be what I would call system safety and understand the constraints. And we're going to build something and introduce it into society. As a civil engineer or a mechanical engineer, you don't get to just introduce something because you had a cool idea. There's a burden on you to sort of understand the way that the thing that you're making is going to work. And the reality is that's really hard in a new discipline, and there's sort of a difference between a new sort of idea or a new technology and a new engineering discipline. And so I've sort of taken this position that because of the society scale impact of these systems, that we don't just need people building new products, we need people building new engineering, like a new field that can handle the complexities of the system. And so I've sort of connected with others, gone back to some of my academic roots, and found people who believed in this vision and sort of started to lay the groundwork for engineering of complex systems. And in my team, that means that we have people from the sort of AI multi-agent systems like I came from. I did a little bit of decision science work because I came through Penn, where we have the robotics lab, and we have Wharton, and there's a little bit of overlap. We also have people who've worked on supply chains, civil, mechanical, and aerospace systems, where there's a much sort of standard sort of burden of engineering ethics that is just expected. We have 2 professional engineers on the team. That is a basis for understanding the interconnection between the real-world systems and the ones that we're adding through technology, and actually including an understanding of biological and ecological systems. We have an anthropologist on the team who works with user experience and works with venture capital and sort of understands the way that our technologies are funded and how they influence us. And ultimately, between the sort of economics team members, the mixture, we have this overlap of data science, and people laugh a little bit because data science in many companies is like the top of the food chain in terms of smart people, and it's like, go find the data scientist. We have an overlap where everyone's common denominator is that they're a data scientist, because they came from these engineering scientific fields where they really couldn't do their job unless they were able to iterate through experimentation and understand, well, I made this, I thought it was going to work like this, but then I made something and I evaluated it, because I don't get to put it out into the world until I have a pretty high degree of trust in what I'm going to get. And the real challenge, though, is that in this field, you don't know. So you need to work on things from a really iterative perspective. And so we work with a basic scientific framework. You theorize, you design, you sort of write out equations, and you say, here's how I think this is going to work. And we've built up some differential equations-based frameworks that are consistent with the natural world, and we use them to characterize what we think is going to happen. And then we simulate, so we do these sort of numerically, computationally empowered thought experiments. But then we sort of build prototypes and test things, and we don't go raise lots of money. We just test them and figure out how it works. And then if and when something works, we try to build it and move forward. And I think this is really important because the space, at least the blockchain space, has taken a more of an internet product development, rapidly get it out approach. And I personally don't think that it's consistent with the level of rigor required for things that can influence the way societies work. And so, part of the reason that I'm excited is because we can change things and make them more common and more coordinated. But there's a burden there because of the lack of predictability. You can't just throw something out there that you hope it's going to work. And so we've built out some internal processes for doing engineering that are very consistent with these engineering disciplines. But this feedback loop between humans inside of the system means that you can't just use differential equations, or you can't just use frameworks that were designed for systems in the real world, the environment only. You have this closure over the behavior, and there's some really nice mathematical properties that you can derive that help you understand this closure, but it requires sort of a game theory and controls and some mathematical expertises that allow you to represent the feedback loop and handle it. In general, that's difficult. It's part of the whole complexity science discipline. We have this framework, though. We specify how the world works, and then given that, we specify how people would act, not their actions, but the strategies that they would use as a result of the way that the world works. We can configure systems across those 2 parts and then test them in sort of both a simulation framework and then later with what we call an emulation framework, which uses the real code. So ideally, before you would put it into the public, you would go use the simulations to do design, take the designs and then put them into code, then use the emulations to test how it would work if it were in the real world. And then and only then are you comfortable enough to put it into the real world because of the impacts it may have on society. So we can kind of see how intelligence has evolved in practice at these kinds of systems where we're now pushing from sort of this human decision-making aided by machines, which is sort of like last era. We're kind of transitioning through this sort of machines making decisions, but ultimately they're aided by us, whether we realize it or not. We're throwing lots of data in. We're saying, hey, take me here. Someone else is saying, take me there. A machine is taking the information from us, making a decision on our behalf and coordinating us. But it's still, in this case, I'm talking about Uber Pool, which is still a centralized orchestrator. But then we're moving in a direction that is more consistent with sort of decentralized intelligence, swarm intelligence, where we want protocols so that when we follow them, we just connect and talk and engage, and the output is a coordinated action. And this is actually highly common in biology, and it's the reason that we use sort of biological systems, including bird flocking, to model coordinated behavior for robotics purposes. And so I'm going to sort of bring us near the end here by pointing out that when we did create these coordinated systems like the ride sharing, we actually had some unintended consequences there too. And they're minor compared to some of the potential unintended consequences, but we took our transportation network, all the cars and the roads and the behaviors, and we added in this economic element, and people started paying each other to drive them around. It's a little bit more decentralized. But suddenly, people stopped using the public transit as much. And so there were actually some externalities on this that we don't always acknowledge directly, right? I would say maybe it's better, but in the long run, there's extra congestion on the roads because people aren't using the public transit. Maybe we build less public transit because people use less public transit. In the long run, we might actually create a significant amount more pollution because we've sort of created a local optimizer where we've made some improvements that we all really like at the cost of maybe some global improvements, which would be, hey, now we all use public transit. Like, we moved farther away from that. And so you could say that's an unintended consequence. I really doubt that the people who sort of made Uber in the first place stopped and thought, man, if this works, no one's going to use public transit, and we're just going to create more pollution. But when you actually zoom out far enough, you can actually see those unintended consequences. And it sort of undercuts the reason that we have to do this engineering. And then lastly, that that's always going to happen sometimes. So we have to be evolutionary even up a level. Like, we need to be able to evolve the thing that we made, but we aren't necessarily going to evolve it centrally. And I think that's the real challenge that's facing us in the future. And people like to talk about governance. I personally view governance over software as a form of social sensor fusion. I'm doing some research on the subject now. But I think the critical element here is that because there can be unintended consequences, even if we do all of that rigorous engineering work to feel really confident, then maybe we're going to make something that's not destructive, but we still are probably going to have to evolve it to the future context. So we need to make things that they themselves can change, and I think that's sort of where we're really going. One of the most important things that we could be researching right now is understanding how to do that. So thank you very much.
Thank you, Michael. I warned you it's going to be complex stuff, and what I got from your talk is that we shouldn't take our responsibility lightly, that we really have to think about all the laws of physics that are behind decision-making for people before we design our systems. Is that what you did with SweetBridge, or how did it?
So with SweetBridge actually was one of the first times that I realized that you could encode a natural law in a smart contract design. So I created a design called a discount token, which was essentially a resource sharing algorithm where you assume you have some service that's going to cost money, but you want people who are participants and who have some form of membership to actually spend less, but the system also has cost, so you have to maintain a conservation in the sense that you always make enough money to maintain the shared service, and so it actually redistributes discounts based on congestion in a sense. If lots of people come at the same time, then you get less of a discount, but if there's very few people coming and there's less use of the discount token, then the power of the discount is higher, and so it actually creates sort of a natural law over a specific requirement, and it makes it a little bit more dynamic, so it can be a little harder to understand at the UX level. So one of the things that we're learning is that we kind of have these cognitive trade-offs where the real world is sort of responsive, and so, but sometimes a little harder to work with. So I guess what I'm saying is I'm really excited about this, but at the same time, the designs are we're just figuring out how to do it. Like we can make a thing that has a natural law, but then like the next question is whether or not people understand it and can use it, and do we need to add other layers? Which brings me to the layers, right? We were trying to say, I talk really fast right now.
No, yeah.
I'm like excited about it. The answer is we designed something for the first time that had a real state feedback law embedded in it, and therefore it respected a property always. But then at the cost of consistency in another way, because it meant my action depended on the state. And so if I don't know whether it's going to be congested, I show up and it's congested, and I'm like, oh, I didn't get a big discount.
I think it's what the movie that we started with said as well. Like, it's the way we move forward if we're prudent. And I think that's what I get from your talk, that we should be prudent and really think about the systems that we're building, because they could change society. Yeah. So we have to think about it well and use some science to actually...
I would say that's probably the real message, is that like this is an inherently iterative and scientific process. And so, going back to founding a company, I founded a company to focus on building the tools and patterns and structures to do a good job. It was like, this is really important, but we don't know how to do it. So instead of picking a project really and building something, what I learned was we're short on tools for analysis, we're short on the understanding necessary to do proper engineering, so double down on what we need to do it right, as opposed to focusing on sort of, as we said earlier, like winning in the sense of ego sense, right? Like I work on a ton of projects actually, and I want all of them to succeed, and my effort goes into what tools it takes for projects to succeed.
And at least we have a lot of scientists here today as well, so I think that worry of taking scientists or science with us, we dealt with that. So thank you so much for your inspiring keynote, and thank you, Michael.